All right, in this section we're going to study triangles. We've already studied right triangles pretty extensively in the trigonometry chapter, so we're just going to take a more general look. So we have triangles formed by 3 points we call vertices, which is the plural of vertex. And we can classify triangles in a couple of different ways. If we classify them by sides, then a scalene triangle has 3 different side lengths. If there are 2 equal side lengths, then that triangle is isosceles. These little dashes, sort of tick marks on the sides, indicate which sides are equal to each other. And if a triangle has all sides of equal length, we call that an equilateral triangle. Now, we already know that the angles in a triangle add up to 180 degrees. So if we have an equilateral triangle, it's not hard to show that each of the 3 angles has to be the same as well, and they're all 60 degrees. Moreover, in an isosceles triangle, if you have 2 sides that are the same, then the angles that are opposite those 2 sides, those have to be equal to each other. We can also classify triangles by their angles. So an acute triangle has 3 acute angles. A right triangle has 1 right angle, and an obtuse triangle has 1 obtuse angle. So it has 1 angle that's between 90 and 180. And this fact at the bottom, of course, we're already very well aware of. Similar triangles. 2 triangles are similar if the corresponding angles are equal. It's important to note that the lengths of the corresponding sides don't have to be equal. Basically, one triangle is either just a scaled up or scaled down version of the other triangle. It's true that if 2 triangles are similar, we know that their corresponding angles are equal. That's sort of part of the definition. But also their corresponding sides are proportional. So if either of these conditions are met, these conditions numbered 1 and 2 here are met, then so is the other, right? These 2 things are kind of equivalent to each other. So in example 3.7, they tell us that these 2 triangles are similar, and we're going to use that to find the length of side B prime C prime. So we know the 2 side lengths here they've given in the figure on the left, and we want to know this length here, and I'm just going to label that as x. So since they're similar, we can set up a proportion. We know that the corresponding side lengths are proportional, so x, B prime C prime, that corresponds with the length BC over here, so I'm going to make that ratio x over 12, and I have a pair of known corresponding sides. I know both of those lengths. So when I set up this ratio on the other side, I just have to make sure it's the same triangle that goes on top. So I got to put the 6 on top over 8. And now, of course, we can solve simply by multiplying both sides by 12. And 6 times 12 divided by 8 is 9. And there are units here, so I'm going to make sure I put on the appropriate units. That would be centimeters. In this next one, we have a ramp that's going to be built so it reaches a height of 1.5 meters over a horizontal distance of 4 meters. So those are the lengths they've given us. 2 braces are equidistant from the ends and each other, so I guess we kind of cut the 4 meters into thirds, and they're used to support the ramp. We want to find the height of each brace. So I'm going to just label them both. The short brace I'll call X, the longer brace I'll call Y. And we want to find each of those lengths. So look, we really have 3 triangles here. And they're all nested, right? They all share that angle A. So I'm going to just draw these 3 triangles out separately. So here's the little triangle at the end, A, G, B, They share that angle. These are all, these braces are you put in a brace, it's going to be perpendicular to the bottom. I think that is a reasonable assumption to make. So they actually all have to have all the same angles, right? They share the same angle A because they're nested, and they have a right angle. So that means this other angle at the top, those have to be equal as well. So this is length X here. And since these braces are equidistant, or equally spaced out, this length at the bottom has to be 4/3. The slightly bigger, kind of middle size triangle, we've got A and then F and C. So another nested triangle, there's the length Y. And then the bottom, again, these are equally spaced, so the length from A to C is going to be double what it was from A to B, so that's 8/3. And then we have one more triangle. This is the one this is the big one, the big triangle where we know 2 side lengths. So we know this is 4 along the bottom, that's 1.5 vertical side. So we're just going to set up a couple of equations. Let's say we want to find x first. Well, x corresponds to, that's the vertical side, so it corresponds to the vertical side 1.5, and x over 1.5 is equal to, and then I'm going to form a ratio using the sides of corresponding sides, the other 2 pair of corresponding sides. So 4/3 divided by 4. We could solve for x by multiplying both sides by 1.5. So 4/3 times 1.5 divided by 4. And I get 0.5 meters. And to find y, we'll just do the same thing, only we're going to use the same pair of known sides, right? Side y corresponds with that side. The 8/3 corresponds to the side length 4. So y over 1.5 is equal to 8/3 over 4. And again, we can solve by multiplying both sides by 1.5. All right, 8/3 times 1.5 divided by 4 will be 1. So 1.0 meters. Okay, next we're going to just do a couple of problems related to perimeter and area. Perimeter, there's not a lot exciting about perimeter, right? You just add up all the side lengths of the triangle, that's the perimeter. It's true for any two-dimensional figure. The area of a triangle can be given by a couple of different formulas. One formula is the one that you're probably most familiar with, the 1/2 base height. You may have seen that before. What's important about this is that 1/2 base height, the height is always the length of the perpendicular line from the base to the opposite vertex. So this perpendicular, that's really important. Height always refers to like a perpendicular height. So the one as it's shown. And depending on the orientation of the triangle, if you draw that perpendicular height, maybe it falls inside the triangle as we see in the definition, or if you look down here in example 3.9, the triangle on the right side, that height is, the way it falls is actually outside of the triangle itself. It just has to be perpendicular. Now, if we know the height, right, if we know the measure of that, we can use 1/2 base height. It's pretty easy. If we don't know the height, but maybe we know all 3 side lengths, then you can use Heron's formula. it looks like this. We have a square root of a product of four things. First you find half the perimeter, right? S is 1/2 of the sum of the lengths. So you take the perimeter, cut it in half, and that's S. And then you multiply four things. You multiply S, and then you take turns subtracting each side length from S to get the other factors inside that radical. If you have the height, obviously use 1/2 base height. That's the easiest. So in example 3.9, these two triangles have the same area. We could see they have the same height and they have the same base length. So the area is 1/2 base height, so that's 1/2 times a base of 14.3 centimeters times a height of 8.25 centimeters. Now I like including the units when I write this out just because it gives me a nice reminder of what my units are going to be when I'm done. So if I multiply, so 1/2 times 14.3 times 8.25, I get 58.9875. And my units, you can see here, I'm multiplying centimeters times centimeters. So centimeters times centimeters is centimeters squared, which makes sense, right? It's an area, so it should have squared units. Now, if I were following the rules of significant digits, if these are kind of measurements and I should be rounding appropriately, I'll just note that these all have 3 significant digits. So if I round my answer to 3 significant digits, I get 59.0 square centimeters. We'll do one more here. We want to find the area of this triangle. Now we don't know the height, so we have to use Heron's formula, but that's no big deal. It's a little bit more work, but it's pretty straightforward. So first I'm going to just find S. So that's 1/2 A plus B plus C, and maybe I'll call this one A. I'm just going to label these sides. So 1/2, 1.8 plus 3.2 plus 4.1. That's 4.55. And then, so these factors, right, that we need inside the radical for Heron's formula. One is S, which I found, and then I need S minus A, S minus B, S minus C. So I'm just going to find each of those. And so let's just bring this up. So 4.55 minus 1.8, that's 2.75. 4.55 minus 3.2 is 1.35. And 4.55 minus 4.1, that's 0.45. Okay, so I have the rest of these. Now I'm going to just plug in these factors into the radical. 4.55 times 2.75 times 1.35 times 0.45. You get 2.757 approximately. Now this is area, so it should have squared units as well. And I didn't write out the units in this calculation, but like let's say I did, right? I've got meters times meters times meters times meters. And it looks like we have meters to the 4th power, but that's inside a square root. So I got a pair of the same unit here, so that's like a single meters unit outside and another pair of meters units inside, so there's another factor of meters outside. So meters to the 4th underneath the square root, that's meters squared as it should be.